Welcome back. In today's explainer, we're going to unravel the totally fascinating science behind, well, literally every single noise we hear. From the gentle rustling of leaves outside your window to the blaring siren of an ambulance rushing by, we're going to explore the physics that makes the whole shebang possible. We're drawing our core insights today right out of Chapter 7 of our source material. And let me tell you, the mechanics of how sound is generated, how it travels, and just how fast it moves are absolutely mind-blowing when you break them down. So let's decode the physics of the world around us, shall we?
Okay, let's dive into this. Have you ever watched a sci-fi movie where there's this massive, fiery explosion in deep space and it's accompanied by a huge, theater-shaking boom? Well, Hollywood loves that dramatic flair, obviously. But the laws of physics, they have a very different story to tell. So, here is our core mystery for today. Why is it that two astronauts, floating outside the International Space Station, could be looking right at each other, shouting at the top of their lungs, and yet hear absolutely nothing? No way, right? Well, we are going to solve this puzzle by the end of this explainer.
To get to the bottom of this astronaut mystery, here is our mission plan for Chapter 7. 1. The mystery of sound. 2. Good vibrations. 3. The music makers. 4. Traveling through matter. And 5. The speed of sound.
All right, kicking things off with Part 1, the mystery of sound. Let's think back to our astronaut puzzle.
To really set the stage for the knowledge gap we need to close here, picture this scenario in your head. You've got two astronauts. They're outside their spacecraft on a spacewalk, and they're incredibly close to each other. We're talking maybe just a few feet apart. Now, if you were in a coffee shop, you could easily hear someone whispering from that exact same distance. But out in the vast expanse of space, total deafening silence. Even if their radios completely failed and they just screamed right through their helmets, the sound just wouldn't reach the other person. There's this massive, fundamental difference in how we experience sound here on Earth versus what goes down in the void of space. To figure out exactly why this happens, we have to look at how a sound is actually born in the first place.
Which brings us to Part 2, good vibrations.
So to solve our space mystery, we first have to establish the root cause of every single sound, and it really all comes down to this one absolutely crucial concept, vibration. The scientific definition of a vibration is just a speedy to and fro movement of an object. That's it. That rapid back and forth motion, that's the engine of audio. Without this speedy to and fro movement, sound simply does not exist. It is the absolute prerequisite for noise. If an object is perfectly still, well, it's perfectly silent.
To really visualize this, Chapter 7 details a fantastic, super simple experiment. Just imagine placing tiny, lightweight pieces of polystyrene right on a speaker cone. When you connect that speaker to power, like a dry cell, it pumps out sound. And what happens to the polystyrene? It starts jumping and dancing around frantically. That's because the speaker cone itself is rapidly moving to and fro. It's physically vibrating. But hey, you don't even need a speaker to test this out. I want you to try this right now. Take your fingers and gently place them right on the front of your throat. Now speak a few words slowly. Do you feel that? That little trembling against your fingertips? Those are your vocal cords. They're basically membranes in your throat that are rapidly vibrating to produce the sound of your unique voice. If you talk a little louder, you'll actually feel that trembling amp up. You are, quite literally, a biological speaker cone.
Moving right along to Part 3, the music makers.
Now that we know sound absolutely requires physical vibration, we can look at how instruments actually manipulate this to create art. And this brilliantly illustrates how versatile vibrations can be. When you look at musical instruments, they all follow that same fundamental rule. They must vibrate, but they do it in just wildly different ways. Take the guitar or the violin, for example. When you pluck or bow a guitar, it's the physical, tightly wound strings that are doing that speedy to and fro movement. But then, think about a flute. A flute doesn't have strings. It doesn't have a drum head you hit. So what exactly is vibrating? Well, it's the air itself. By blowing into the flute, you are forcing the actual column of air inside the instrument to vibrate rapidly, which produces those high, sweet notes.
In fact, we can categorize instruments strictly by the physical part that's doing the vibrating. Guitars rely on vibrating strings. Flutes and other wind instruments rely on vibrating air. Meanwhile, percussion instruments, like a standard drum or a traditional tabla, produce their booming sounds through tightly stretched membranes that vibrate the moment they're struck. It's really all the same physics, just applied with different engineering.
Okay, Part 4, traveling through matter. We're getting closer to our astronaut answer.
We've established how sound is made, right? But it also has to reach our ears if we're going to crack this astronaut mystery. And this brings us to a really classic, brilliant scientific demonstration known as the bell jar experiment. Here is how it goes. Step 1, you place an electric bell inside a sealed glass jar and turn it on. Easy enough, you can clearly hear it ringing through the glass. But in step 2, you connect a vacuum pump to the jar and slowly begin sucking all the air out. As the air gradually evacuates, something amazing happens. The ringing sound gets fainter and fainter and fainter. Finally, in step 3, once the jar is completely emptied of air, creating a true vacuum, the ringing fades to complete and total silence. The bell is still physically vibrating in there, but you hear absolutely nothing.
So, the crucial point is this: sound absolutely needs a medium to travel through. It literally needs physical matter, particles, to pass those vibrations along, kind of like a microscopic relay race from the source right to your ear. Inside that bell jar, when the air was removed, there were simply no particles left to carry the vibration. And boom, there is our answer to the astronaut puzzle. Space is a vacuum. It's this empty expanse totally devoid of air or any thick atmosphere. Because there is no medium in the vacuum of space, there is literally nothing to carry the vibrations from one astronaut's vocal cords over to the other astronaut's ears. No air equals no sound, just total silence.
But you know, we shouldn't think that air is the only medium sound can use. Far from it. Sound is incredibly adaptable and will happily propagate or travel through all sorts of states of matter. We just established it travels through gases like the air in a room, but it also travels wonderfully through liquids. This is exactly how dolphins and whales communicate across vast stretches of the ocean. The water molecules themselves serve as the medium carrying their clicks and whistles. And sound even travels through solids. If you've ever built one of those makeshift telephones using 2 empty yogurt cups and a long, tightly stretched 10-meter thread, you've actually proven this yourself. When your friend speaks into one cup, the sound vibrations travel directly down that solid thread, right into your ear on the other side.
Which brings us to our final section, part 5, the speed of sound.
So we know sound can travel through gases, liquids, and solids, but does it travel at the same speed through all of them? Now, what's really interesting about this data is how drastically the speed jumps, depending entirely on the medium. When sound travels through air, a gas, it moves at about 330 meters per second. I mean, that's fast, for sure. But when it enters water, a liquid, it speeds up massively to 1,500 meters per second. And when sound travels through a solid, like steel, the speed just absolutely skyrockets.
4,500 meters per second. Seriously, think about that for a second. Sound moves through solid steel more than 10 times faster than it moves through the air we breathe. Why? Well, because the particles in a solid are packed so much more tightly together, allowing those vibrational relay passes to happen incredibly fast. This is actually the scientific reason why, back in the day, people would press their ear against a solid steel railway line to hear if a train was coming from far away. They could hear the vibrations through the solid trackway way before the sound could ever reach them through the air. Now, as Chapter 7 wisely notes, putting your head on a train track is a very risky activity, so definitely don't try that one at home, but the physics behind it is undeniably fascinating.
Before we wrap up, we really have to compare the speed of sound to the absolute speed champion of the universe, light. Even though 330 meters per second in air sounds super fast, it is painstakingly slow compared to light. This is exactly why, during a thunderstorm, you're always going to see the brilliant flash of lightning first and only hear the booming thunder a few seconds later. The light and the sound are created at the exact same moment, but the light wins the race to your eyes long before the slower sound waves finally hit your ears. The exact same thing happens if you watch a distant cannon fire. You'll see the plume of smoke immediately, but you'll have to wait a beat to actually hear the blast.
Well, we've covered some incredible ground today. We've learned that sound is born from vibration, relies entirely on a medium to travel, and changes speed dramatically depending on what it's moving through. But I want to leave you with this final, provocative thought. We just learned that sound travels the absolute fastest, a staggering 4,500 meters per second, through solids. And right now, there is an entire world of solid rock, steel, and earth right beneath our feet. So what hidden, high-speed sounds echoing through the crust of our planet are we completely missing out on at this very moment, just because our ears are stuck up here in the slow, gaseous air? Thank you so much for joining me on this explainer. Keep questioning, keep observing, and never lose your curiosity about the incredible physics shaping our world. Catch you next time.